This is a rotating machine system in which we have a self-excited DC motor which is driving a synchronous machine which is configured as a three-phase synchronous generator. The motor's power source is one of our primary DC supplies. Here we have a Hampton DM100 DC machine that is configured as a self-excited shunt DC motor. The bottom two terminals are the input DC power goes through the circuit breaker switch to the internal power terminals. Notice the positive and negative in the routing. The positive input is routed to the armature, and that is also going to an ammeter to measure the current, and coming back from the ammeter to the field circuit where it's run through a field rheostat, a variable resistor adjusted on top here, and that is in series with the actual shunt field winding that's wound on the stator of the machine. Through the shunt field winding, we complete the negative circuit path to the armature and back to the source. On the synchronous machine, configured as a motor, our ABC three phases are input here from the load side or source side of the circuit breaker, and from there we jump them up to the three windings on the stator of the machine. One side of the windings is tied together, which goes back to the source neutral, which makes this a Y-connected three-phase motor. Also very important in a synchronous machine is the excitation winding or field winding. The DC current applied to a synchronous machine creates the internal rotating magnetic field, which creates torque and rotation in a motor. The generator's net load is using this RLC100 three-phase general-purpose resistive reactive load, which is configured as a Y-connected impedance. First, we're going to start up the DM100 DC machine, which is configured as a self-excited DC motor. First step, important in starting up the DC motor, is have the circuit breaker initially off, have the excitation field rheostat in its minimum position, not maximum, in a motor startup. Our DC power source circuit breaker is on, our adjustment knob is at 0, and we're going to slowly ramp up the voltage until we get rotation. We'll bring the voltage up to a nominal level. The speed of the motor can be adjusted by varying the field rheostat and using the tachometer to read the drive shaft speed. In the startup of the three-phase synchronous generator, again the circuit breaker should be off initially and the load should be at 0 value for when the circuit breaker is turned on. The synchronous generator, before the load is connected, once you are driving it, you should adjust the excitation to get the voltage operating at a satisfactory level for the load before switching the load on. A voltmeter-ammeter pair is connected to measure a per phase output of the synchronous generator. In this case, A phase to neutral on the voltage and A phase line current. In a synchronous generator, the magnitude of the AC voltage is controlled by the DC excitation current. Notice how varying the DC excitation current, increasing it, increases the voltage output on the top meter. I'm going to adjust it to a nominal 120 volt output. At this point, the load can be varied to show the load current on the bottom meter increasing or decreasing. And as you decrease load in this case, the output voltage increases and can be compensated by adjusting the DC excitation again.